Okay, guys. Okay, so this is going to be on acid and base balance, and this will be the last thing that'll be on your test. So make sure you guys take some good notes on this one, and then we'll talk a little bit at the end of possibly the next video what'll be just essentially on your test and how your test will be kind of sort of formatted, especially the fact that we're going to be doing this at a social distancing and you're going to be doing it online. Sorry, it's the best I can do for you at the moment. Okay? So we're going to talk about acid-base balance, and all that really concerned is that whenever we're talking about acids and bases, we're only concerned with our concentration of hydrogen ions. So how do we know what's the correct amount of hydrogen ions that we should have in any portion of our body? Okay, we need to make sure that this stays correct, that this stays in balance. Okay, if we don't state this, we can easily become fatal because that's how much having a lower pH can be. It's why whenever you're in a chemistry lab, you don't drink anything because you could drink an acid and kill yourself. That's the idea. You're deviating from a normal pH range, and that could be fatal. That's why you don't drink sulfuric acid. Okay. So whenever we're talking about pH, we're only looking at whether or not we're only looking at our hydrogen ion concentration. So anytime we've got acidity or alkalinity, we're going to be talking about pH. Now pH starts at a neutral situation of 7. Anything below 7 is considered acidic or the acidity, okay? And that's going to be have more hydrogen ion concentrations. Okay, so anytime it's an acidic, you're going to have a higher hydrogen ion concentration. Okay, so acidosis, that's going to be whenever you have an arterial blood pH that's less than 7.35. That means that it has more hydrogen ions. Okay, when we're looking at alkalinity, that's going to be higher than our pH of 7 and means that we have less hydrogen ions. Not as many. Okay. So alkalosis means that we have an arterial blood pH greater than 7.45. Okay, so our range in between there that's good is between 7.35 and 7.45. Okay, this is our typical pH range of anything as an example. Think of this kind of hydrochloric acid, sulfuric acid, though any strong acid. If you've ever heard of a strong acid, if not, no big deal. I'm sure you guys have all taken chemistry, so you know what a strong acid is. Now you can remember this. I always remembered it that I've actually had a sulfuric acid spilled on me um, when I was working at Eurofins. Now, thankfully, it was on my lab coat, but it actually ate through my lab coat and onto my shirt. And I said bye bye to that shirt because that shirt actually had a hole in it the next time I looked at it. So, yes, it was only a small amount and it was very, very minuscule, but it ate through the lab coat and my shirt. That's how serious it is. And sodium hydroxide, I always think of Fight Club. Okay. So, whenever within our body we have some pH influencing chemicals that are just naturally occurring, for instance, carbonic acid. So, that's going to be anything kind of really once carbon dioxide gets into your body, it becomes an unstable carbonic acid. So, with glucose metabolism, especially when we're looking at cellular respiration, we are making carbon dioxide, and therefore it's going to be produced as carbonic acid. Typically, it goes from carbonic acid to become a bicarbonate ion, which travels through our body. Okay. We got lactic acid, so that's typically done through fermentation, and that would be an example of that would be something that you kind of get as a byproduct with making alcohol. So the same situation happens within your body. That's why you feel so like blah whenever after you exercise because your body hasn't been able going through cellular respiration. It's been going through anaerobic or fermentation. Okay. Sulfuric acid. So whenever you add oxygen and a water molecule to a sulfur in your amino acids, you're going to get a sulfuric acid. And that's a very strong acid, so it can easily lower your pH. Phosphoric acid. So this is when you have phosphoproteins, again, proteins that have amino acids that have phosphate groups on them, or you have your ribonucleotides. Again, your nucleotides contain a phosphate group. They're broken down and that phosphate group has gone ahead and merged with some hydrogen ions to give you phosphoric acid. Okay. You also have acetic ketone bodies. The biggest idea that you can remember with this is think of the ketone diet. This is what you're trying to go for. Okay, and you have any, sometimes you'll have acid forming or base forming minerals. A lot of times you'll excrete those through your urine, and that can be a good indication. It's why a lot of times, depending on what type of urine analysis people are doing, they have to lower the pH. So they'll add acid to your urine to make sure that everything stays in solution so they're able to detect it using their materials and their instrumentation. Okay. So when we look at types of pH control mechanisms, the biggest and easiest one to remember is there's always going to be some type of buffer that'll go ahead and prevent this from. That's the first kind of line of defense that'll prevent a pH change that can be dangerous. And realistically, your blood's a buffer. Everything that can carry, carbon dioxide or an acid of some sort, your stomach acid technically is a buffer. Any of those, they're considered buffers. They're mostly chemicals. And the idea here is that you can add certain hydrogen ion concentrations, usually about up to 1 pH level, and nothing will really happen. The pH won't really change. If it does change, it won't be without of your, range of that's good. After that, though, once it hits the chemical portion, once it hits that 1 pH range, now it's going to start to fall off and become really, either acidic or basic, whichever way you're going. In this case, then we go to a physiological buffer, and that's kind of like our secondary defense. This is the idea behind this is it's supposed to prevent the harmful shifts that chemical um, buffers cannot do. Okay. Again, there's one thing that we need to talk about pH shifts. They won't immediately be halted because they will occur within your. So basically, the third step, the third line of mechanism, if we have something that's not taken care of by our buffers, we will go ahead and then change the way that we're breathing because most of the time that has to do with carbon dioxide. And so, therefore, if we're getting rid of all of our carbon dioxide, or if we're getting more oxygen in order to maintain our carbon dioxide, then therefore we're going to have our changing in a rate and depth of breathing. So therefore, there's three different ways in which we kind of control pH, and that's going to be through buffers, through our respiration, and through kidneys. Our kidneys get rid of it. Remember, during our filtration process, we oftentimes take out certain things, but we put other things in. Remember, you saw that ammonia molecule going in and getting, excreted that way. Okay, so all buffers are going to be consisted of two things: a weak acid and its base salt of that acid. Okay, so therefore, if we talk about this, we would be like acetic acid and acetate, because acetate is the basic salt of acetic acid. So there's a lot of times we have buffer pairs that are going to be present. The biggest ones that you kind of need to remember are there's bicarbonate ion or bicarbonate pairs. Again, so that's very important to remember. We have plasma and protein pairs. Again, very important to remember. And then we have hemoglobin pairs and phosphate buffer pairs. Remember, we've got phosphate is going to be something that's kind of shown up a lot. And that's because of the fact that we have a phosphate group on our nucleotides, and ATP is consisted of 3 phosphates. Okay, so phosphate kind of just is all over our cells. Now, whenever we talk about preventing changes in pH, the idea here is that the buffer is whatever, if we add a strong base to it, we're adding more hydroxide ions, and therefore they're going to react with our hydrogen ions from our base, and therefore kind of be canceled out. And so, therefore, instead of the strong base, we now have a weak base. Whenever we look at a strong acid being added, it's going to react with the hydroxide ions of our base, and therefore we're going to have a weaker acid that's now going to go because there's not going to be a whole lot going on. Okay. Um, so the idea here is that this can kind of help, buffering can help lower the hydrogen ion concentration within our blood so it's not at a dangerous level. Okay. Um, Cellular metabolism, oftentimes we can form carbon dioxide, and if we have carbon dioxide, it's most likely going to go form into carbonic acid, which is what we carry through our blood. The idea here is that can change our pH very easily, but because we have this buffering system, we don't have to worry about that. Some other ways in which we can change this: if this buffering system is not enough, for instance, we have a lot of carbon dioxide being given off because we just ran like a mile and a half or something like along those lines, We have this thing called a chloride shift, and essentially what a chloride shift does, it allows for the carbonic acid to become bicarbonate, and then with that bicarbonate, it can stay as an ion because what will react with the bicarbonate will react with the chloride first, and that's what we call a chloride shift. In addition, we can also have non-volatile acids such as hydrochloric acid, lactic acid, and ketone bodies can basically be taken care of using sodium bicarbonate. In addition, if so, that's kind of a thing that's actually shown in our actual workforce, because if you ever go into a serious scientific lab and if they're using concentrated hydrochloric acid or concentrated sulfuric acid, there's a bucket of sodium bicarbonate somewhere in that lab, I can promise you. And the idea behind that is if that acid gets spilled anywhere on the floor or anything along those lines that's not on the actual top, not in the actual hood, you put sodium bicarbonate on top of that acid, it'll react and become neutral, and then you can just wipe it out. You don't have to do anything else. Okay. Now, the ratio that we ever have with these whole situations is critical, because if we don't have the correct amount of pH within our buffer, it's not going to be good. We're not going to have things. We're going to have alkalosis and acidosis that'll show up, especially within our blood. Okay, so this is an example of how, apologize, how carbonic acid can become a bicarbonate ion instead. Okay, and this is demonstrating how the chloride shift would work. Okay, so whenever we're talking about respiration, the idea behind this is that we have the amount of carbon dioxide that goes into our blood is directly related to the amount of carbonic acid, and therefore the amount of hydrogen ions that we have in our blood. Okay? Because that hydrogen ion reacts with the carbon dioxide to form carbonic acid. So if you have more respirations, you have less carbon dioxide because you're getting rid of it, right? If I'm breathing out a lot more, then I'm going to have less carbon dioxide, therefore less carbonic acid and fewer hydrogen ions, because what am I getting rid of? I'm getting rid of my carbonic acid through my carbon dioxide, okay? If I have decreased respirations, I'm going to have more carbon dioxide within the blood, therefore I'm going to have more carbonic acid, which means more hydrogen ions, okay? So therefore, our respiratory center will adjust to make sure that our arterial blood level maintains in that 7.35 to 7.45 range by either increasing our rate or making us have deeper breaths so that we can decrease our rate of respiration. In addition, we can also have in our carotid chemoreflexes, we can also have some respiratory adjustments based off of what they detect within the blood as far as the pH level. Again, the big idea here, acidosis is going to basically mean that we have a lower pH. If we have a lower pH, we have more hydrogen ion concentrations. So therefore, we're going to hyperventilate. We're going to breathe quickly because we want to get rid of as much carbon dioxide as possible, because more carbon dioxide means more carbonic acid, which means more hydrogen ions. Okay? So that's where we're saying that if you go for a longer time with this, then you can go to the opposite end of the spectrum and produce alkalosis. In this case, then you would start triggering hyperventilation, okay, which would be slower breathing, more deep breaths. And the idea here is that we want to go ahead and save some of our carbon dioxide to make more carbonic acid and therefore have a lower pH, okay? If you do this for a long enough time, you're going to go to the opposite end, right? And you're going to start getting acidosis again. So the idea here is we want to find a good balance between the two. Whenever we're talking about whenever we're talking about gas exchange, remember we talked about how it's all dependent on partial pressures. Well, I kind of lied a little bit, but just for what you needed to know for that was important. But the other thing that kind of plays a role in gas exchange is one, the pH. So whether or not it's at the optimum pH, because if it's not at the optimum pH range, then therefore we need to get rid of we either need to store more carbon dioxide or we need to get rid of more carbon dioxide. So that'll be a thing. Concentration of bicarbonate ions. Again, this will influence pH. and oxygen saturation in the hemoglobin. That doesn't really have a whole lot to play in with what we're talking about with pH, but the idea here is that if you have more oxygen, you have more oxygen that can react with our hydrogen ions, and therefore you can get them to form water, and bye-bye they go. Okay, so urinary controls of pH. So the idea here is that we have an acid-base balance that is going to be eliminated from the kidneys. So this is where we can kind of either eliminate more hydrogen ions while reabsorbing sodium ions. Again, when that's only when it goes towards the acid side, okay? Because sodium's more of an alkaline thing. So therefore, if you eliminate fewer hydrogen ions and you reabsorb less sodium ions, then you're going to have more of an alkaline pH. So your distal tubes and collecting tubes, they'll get secrete and reabsorb basic hydrogen ions and basic ones. Um, Therefore, carbon dioxide diffuses into the tubular capillaries to form carbonic acid. And then you're going to have this dissociates into hydrogen and bicarbonate ions. Okay. Um, Renal tubes, they're going to excrete the hydrogen, potassium, and the reabsorb sodium. Distal tubes and collecting ducts, these guys will actually excrete ammonia. Okay. And if you have the ammonium ion, you're going to have more of a basic ion. Okay. So there's two different types of imbalances. If you have metabolic acidosis, that means we have a large amount of acid that's entering the blood. This can be if all other things fail. So this means that we've gone through all of our first three steps of our mechanisms to prevent any acid-base balances. Then we will look at seeing this situation occur: metabolic acidosis. Metabolic alkalosis, this is when you use too many acids or you do a lot of vomiting. Again, because there's going to be more alkaline things that'll come up within that situation. Okay, any questions, please let me know. Other than that, this is the last video. What we'll kind of do, I haven't written your test yet. However, your test will probably be involving similar to the format that you've had, but it will be written online, so just be aware of that. I have put the date up in Canvas, so check Canvas for the date for your test.